All right. So now we're going to start talking about the metallic structures, and we start with what we call the simple cubic structure. All right. The simple cubic, or SC for short, is the three-dimensional equivalent of the previous example for 2D, where we saw here this kind of AA stacking. So if you kind of extend this to 3D, you get simple cubic. So let's go back. And so this is kind of what it would look like with these equally sized spheres. We can tend to call this the closed pack model. So you kind of see this size and shape of the spheres. But to see the greater structure, sometimes we show this kind of ball and stick model. So the spheres here aren't at to size, they're not to scale, and so they're made smaller so that you can see the greater kind of structure here. And it's a cube because all the sides are equal. So this distance is the same as this distance, which is the same as this distance. So it's a cube. And so basically you can think of it as a cube with spheres at each corner, right? So a little bit about the structure. This is actually incredibly rare. So we don't see metals very much with this packing. And we don't see it because it tends to be really low packing density. So it's not very stable. And so the only element that has the structure is actually polonium, PO, which is radioactive and obviously not a very useful material for the most part. And in terms of what we might call the close packing, so where things are touching, so the close pack direction in this case, those are the edges. So if you look at this space-filled model, you see that they're touching along this direction, which is the same as the cube edges. So that's where we have close pack directions. Another thing we can look at is the coordination number. This is that nearest neighbor concept I brought up in the previous module. So how many neighbors is one reference atom touching? So it's hard to see here because we only see the 8. But if we look here and focus on this red one as our reference point, we see that it would be touching this atom, this atom, this atom, this atom, and then the one up below and the one above. Keep in mind again that these aren't the correct size of the spheres. You have to think of them like this. So they are touching, it's just drawn so that it's not touching. So that is 6 nearest neighbors, or what we term the coordination number. So coordination number is equal to 6 in this case. All right, so I mentioned that this structure has a low packing density, what we call packing density. So I want to get a little bit more to that. So as we go through the rest of the structures, you'll have an idea of what this number means. And so we're going to do some calculations to get there. All right, so the first one is, again, on a quiz question. So I want you to, before we get into this actual calculation, I want you to see if you can come up with it. You know, just think about this structure or any structure. How would you calculate the amount of space that this material occupies? So that's the packing of atoms. So see if you can kind of come up with either a very specific formula or just kind of a general description of how you would calculate this. So it's kind of a brainstorming exercise, and then I'm going to show you the formula that I have. So take a minute, write those thoughts down, and come back and we will discuss. All right, so the way we do it, hopefully you got something close, but it's, I want you to kind of think about it because this is something that you could kind of, make up on your own. Like, you just have to be able to think about how much volume the material takes up as opposed to the volume it occupies, right? So this is how we do it. We do it with something called the atomic packing factor. This is APF for short. And it basically accounts for the volume that the material takes up as opposed to the volume overall. right? So it basically quantifies the amount of empty space, or the amount of filled space, I should say. And so all we have to do, very simply, is look at the volume of atoms, and we're going to take a reference point, right? Because we're looking at a specific volume. So we basically define our volume. And so since this is a simple cubic, let's take that simple cube, right? So this cube is our volume. So that's the total volume of space that we're looking at. And then we're going to look at how much space of that unit cell is occupied by atoms. And so we have the volume of atoms within this unit cell divided by the volume of that unit cell. So that gives us a fraction, a ratio of volume occupied, right? And because it's a ratio, the units, there are no units. And what we're doing here is we're assuming hard spheres. So each atom we're looking at, or ion we're assuming it's a hard sphere. So a couple things that we need to know is the edge length for the cube. We call this A, and as we get more into this, you'll see why we call it, we call it the lattice parameter, and that's tied to some other aspects too. So A is the edge length, commonly known as the lattice parameter. And then we're going to talk about these hard spheres, these atoms, of radius r. So we need to know those two quantities to be able to make this calculation. So I have, I think, a pretty simple methodology for solving these types of problems. So what we're going to do is we're going to assume that the unit cell is defined, right? So we've got it like this. So we don't have to determine what the unit cell is, the cube or whatever other shape. So let's say we already have that defined. So what we're going to do is we're going to determine the number of atoms inside that unit cell, right? So this is already kind of cut off so you see it, but we're going to determine the number of atoms inside the unit cell. So this cube in this case. Then we're going to calculate the volume of those spheres, atoms. There are spheres, so we can use the volume of a sphere equation. And then we are going to calculate the volume of the unit cell, so the volume of the geometric shape. And to do that, we're going to notice that one of these is in terms of A, and one of them is in terms of R. So to be able to compare those, we have to have a relationship. So we're going to use a relationship based on this structure to be able to solve A and R. And this will allow us to solve the APF. All right, so let's get into the next question I have for you on the quiz. So looking at the structure, what is the volume of atoms in the unit cell of this simple cubic structure? So therefore, you got to know the number of atoms to start. So see if you can come up with the number of atoms and then calculate the volume for those atoms. Pause the video, see if you can solve that, and come back and we will discuss. All right, so let's take a look at this problem. Let's see if we can count the number of atoms in here and solve the volume. Okay, it's not written down here. So let's go ahead and do that. So the thing I want you to remember is that we're talking about within or inside the unit cell. So you see that, there's an atom here, but it's kind of truncated based on the faces of the cube, because the rest of this atom is actually in another unit cell. So if we look at this, this is what we would refer to as an eighth, right? So if we think about this, this is 1/8 of that sphere, because we effectively have a fourth of the bottom, and then there's a half, right? So there's, if you kind of work it out, you'll see that it is 1/8 of a sphere. And you can also think about that based on how many other unit cells it would be in. So yeah, you might kind of draw this out and see if you can prove it to yourself that this is 1/8 here. So let me draw this real quick. So that is 1/8. All right. So this is 1/8 of an atom. And so let's count how many we have of these. So there is one of these on each corner, right? And we have 8 corners, right? It's a cube, so we have 8 corners. So we have these 4, and then the 4 below, and we can't see 1 because it's back here, right? So at each corner, there's 1/8 of an atom. So basically 8 times 1/8, right? So this means that we have 1 atom, right? 1 atom per unit cell. I'll just use C for unit cell. So we have 1 atom per unit cell. So even though, you see there is an atom centered here, there's only 1/8 within the unit cell. And so when we're talking about the volume inside this cell, then we only count what's inside of it. And so we have 8 times 1/8. And so that means inside this cube, there's 1 atom because there's 8 eighths. And so when we get to volume, then we have to calculate the volume of a sphere. So if you remember how that's calculated, the volume is 4/3 pi, and then it's the radius, so r, so we're using the same as we used over here, r cubed, right? And since we're only looking at the volume of 1, this is multiplied by 1, right? So effectively the volume of the atoms in this unit cell is this equation here, 4/3 pi r cubed. All right, so I've written over it here, but the next set of questions I want you to tackle is this. So look at the unit cell itself, so the cube, and calculate the volume. And then I want you to do is, think about if this volume of the simple cube depends on the atoms in the unit cell. So answer those questions on the quiz, and then come back and we will discuss those. All right, so you're back, and so let's look at the volume. All right, so a cube, right, has an edge length of A, and we basically, for the volume of a cube, sorry for the handwriting there, but the volume of a cube is the edge length cubed, right? So it's A cubed, right? So that's the volume that we have here. And you'll notice here that it's just the edge length. We aren't accounting for the spheres, the spheres or the atoms themselves. So it actually doesn't depend on the atoms, right? So it's just A cubed regardless. For a cube, it's always going to be A cubed. All right, so now let's go ahead and look at the last part. And that is, we want you to calculate the atomic packing factor. So you have the volume of the spheres in the unit cell. You have the volume of the unit cell itself. And so see if you can calculate the atomic packing factor. Do that and come back and we will discuss. All right, so let's put all of these parts together. So we previously found that we had 1 atom in this unit cell, and 4/3 pi r cubed is the volume of a sphere. And then our unit cell is a cube, so it's the side length A cubed, right? So our atomic packing factor calculation is the volume of the atoms inside the unit cell over the volume of the unit cell. So that means that our atomic packing factor is 4/3 pi r cubed over a cubed. All right. So like I said, in the last step that you need is some type of relationship, because we have r and a, so we can't sort of simplify or reduce this expression. So what we have to do, and this is going to be the same as in any problem we work, is we need to find where the atoms are in closest contact, so where they're touching, right? And so again, this is kind of the ball and stick model, but they're touching along these type directions. So that means that effectively there's no empty space here. There's one radius and then another radius, and then those are touching. So basically we know that 2r equals a for a simple cubic structure, right? So knowing that now, we can plug this in. We can basically now 4/3 pi, and then we're going to keep this, let's keep this as r cubed, and then we have 2r cubed on the bottom. So right now we're going to have an r cubed and an r cubed at the bottom, and so this is going to simplify, and so we're going to have 4/3 pi, and then we are going to have the r cubes are going to cancel out, and then we're going to have 2 cubed, right? So that's 8. And so this is just a number in fractional form. So when we calculate this, we get that this is roughly 5.52. And so this is our atomic packing factor for simple cubic. And so this is going to be our reference point. So basically what this is saying is that 50% of the space in this unit cell is atoms, and then the rest is obviously empty space. So for reference, again, we call this a low packing structure, and so this is a low packing number. And so when we look at some of the ones in the next section, think back to what we have here.